Okay, so today's lesson doesn't necessarily go with the assignment 100% like they normally do, because the assignment that I'm going to give you just has 4 polar application problems, which are not any more difficult just because they have words with them. It just kind of gives you some insight into when that stuff might actually get used. But today, the lesson itself, I just want to kind of give you a little insight into some other coordinate systems. This is not anything that I plan on testing you over or anything like that. I just want to expose you to it because it could be something that you experience before in a science class or like a mechanics class or something in college before you actually experience it in a math class. I don't know. But I just want you to know that these things exist, so it's not just a big shock when all this crazy stuff gets thrown at you. So we've been, up until a little while ago, X and Y was your whole life, and then we learned polar graphing, and there's a whole different coordinate system, right? Well, that isn't it. There's a whole lot of other ones, too. And so this first one right here, the Cartesian coordinates, which is X and Y, but to get three-dimensional, we also have Z, right? And that is something that probably, we've at least talked about before, talked about how if you have X and Y and then Z could be coming off of your paper. So I have this little model right here that represents that. The red is X, the green is Y, the blue is Z, right? So where you are used to seeing like X and Y like this, right? This is X, this is Y. I only have the positive ones because I couldn't find one of these little things that came off all directions. It probably would have made it more confusing anyway, so just the positive part, but the negative does exist, okay? So we've got X and Y, it's what you're used to seeing. You can think about Z coming off, off the board or off your paper like that. But most of the time when you are actually looking at this three-dimensionally, it gets rotated like this, where Z is up and then X and Y are down like it shows right there. Does that make sense to you? So you have an X coordinate, you come out X, you go up Y, there's your two-dimensional, and then you would just go up the Z coordinate and boom, there's your point right there, okay? So then we also have cylindrical and spherical coordinates. And what made me decide that I wanted to show this to you was when Mr. Ackerman and I were talking about polar and, whether or not I could really explain to you at this level when it would be better to use polar coordinates than rectangular coordinates, that sort of thing. So he told me a story about when he was in college, and I think he said it was one of his mechanics classes. What year in college, I don't know. But, all these little smart kids go in there and the professor gives them a problem. And so they go for it, they do the problem, they bring it back the next time, and they have like pages and pages of work, and they're all puffed up like, see, we can do this, we're smart, we all know what we're doing. And so they all have this paper, and they're just there to show the professor how brilliant they are. And he's like, all right, well, you know what, y'all are right, but wow, you did it the long way. And he did it in like 2 lines and was done. And so what they had done, it was a problem about cars coming down out of a parking garage. And so, you rotate to come out of the parking garage. But there's even some where, like, you go to the end and then it kind of looks like this at the end. But either way, you have to, you go down, you go up like this. And they had done it when they had pages and pages of work, they did it in X, Y, and Z coordinates, so the rectangular coordinates that, made sense to them. They didn't do anything wrong. They did it right. They just did it the hard way. He said, well, if you'd have just converted it to the cylindrical coordinate system, then it would have just been real easy, because there's a cylindrical coordinate system, and that's basically what was happening was you had like that cylindrical model of coming down out of a parking garage. So I have a feeling that that was the professor's favorite problem that he always used at the beginning of the year to knock everybody down a notch, like, yes, you're smart, but guess what? There's other ways to do things. So I want to show you what the cylindrical coordinate system looks like. And these two, the cylindrical and the spherical, kind of relate to the polar a little bit. So you've got R, this is phi, and then Z, but it could be theta as well. So if you look at what it's showing you up there, right? So I'm going to come out and I have, so this is like my point, you can pretend, right? So this is my R, I have my radius. I'm going to swing out an angle, and then I go up the Z coordinates, and I can end up at the same point as when I did X, Y, and Z. It's just putting that angle in there as an angle of rotation to get my cylinder. Because if I have a radius, and then if you think about this, this is just a fourth of it, but I could go all the way around and make a circle, and then go up, and I get my cylinder. Make sense? So there's a cylindrical coordinate systems. Then there's also spherical coordinate systems, which is going to include 2 angles. So I would have my radius come up, then I would swing an angle down here, and then swing an angle over here, and I could end up at the exact same point. So there's different ways to get to those places, whether you want to use spherical, Cartesian, or cylindrical, depends on the situation that you're in. Again, I don't expect you to remember all this or know how to do all this. I just want you to see that these things exist, and you've kind of talked about some of these at some point in a social studies class when you talk about map projections, because there's like a cylindrical map projection as well, right? There's different ways to project those things, and they have coordinates for all of this stuff. Remember, we live on a sphere. These spherical coordinates can be very, very important to us. Down here at the bottom, I just gave you kind of a different view of them. So it talks about global and local coordinate systems, because you can, change the coordinate system you're in depending on the problem that you want to do. But what it says is when you define it, basically the global Cartesian system is by default. Okay, but then sometimes you want it to be in other systems other than the global coordinate system, and they are predefined as Cartesian, cylindrical, and spherical. And then it talks about numbering and all that. I just left all that weird numbering and stuff here. But notice that there are 3 different ones for the cylinders, because it depends on whether you want the cylinder to have the z as the height, or the x as the height, or the y as the height, again, depending on what you're trying to do with that. And remember, these do have negative aspects as well. Like this is just a chunk of the sphere, but the negative parts of it make the entire sphere. It's just showing you the positive parts of it. Okay, any questions? Did y'all know these things existed? Okay, so, and you're not going to get, as far as the math courses, it's not until Cal 2 that you start even talking about polar or some of this other stuff. But again, these things could pop up in your science classes or in engineering classes, things like that, where you start to learn these things a little bit. So I just want you to at least know that they exist. So it's not just mind-blowing when it gets there. I'm not testing you over it, just wanted you to see it, think about it, that sort of thing. Okay, we good? Now on the back, these are polar applications. Well, the first one's a polar application that we're going to work through together. You are totally capable of doing it yourself, but I didn't want you to have to graph this one, and I just figured this was a good example because it is going to take a little bit of thinking here. So it says polar equations are used to model the paths of satellites or other orbiting bodies in space. So there's one application right there. NASA definitely uses it. Suppose the path of a satellite is modeled by this equation right here, where r is measured in tens of thousands of miles with Earth at the pole. So Earth is the pole. That means this is Earth right there. So part A says to graph it. I didn't want us to have to graph it. It would have been all wonky and whatever, and we hadn't really talked about ellipses anyway. And so this r equals, this is basically r of theta. Think about that. It's like f of x type of thing. So we have this graphed. Then it says, determine the minimum and maximum distances the satellite is from Earth at any time. Well, the ellipse shows the path of the satellite, right? So the minimum distance, wouldn't that be right here? And the maximum distance would be right there. If I can draw. Make sense? This would be my maximum. This would be my minimum. Since Earth is the pole, both of those are a radius as far as polar coordinates are concerned. Does that make sense to you? So I want to figure out what they are. How could I find the minimum distance there? What do I know that I could use? Because I don't know what the radius is. That's what I want to find. Do I know theta? What's theta at that? Pi halves. Right here, this is pi halves, right? I have this equation, so I can just find r of pi halves. That's going to give me 4 over 4 plus 3 times the sine of pi halves. 4 over 4 plus 3. What's the sine of pi halves? 1. So this is 4/7. So is my answer 4/7? Tens of thousands of miles. Have to multiply it by 10,000. Right? Which means that obviously that would be something we would have to, well, you get an exact answer, but I'll give you what it is. It's about 5,714 miles. So that's the minimum distance that satellite is from Earth at any given time. So then we need to find the maximum. What do I do for that? Same equation, but my angle is what? 3 pi halves. So that's equal to 4 over 4 plus 3 times the sine of 3 pi halves. That's 4 over 4 plus 3 times what? -1. So that's 4 times 10,000, which is 40,000. And that's the maximum. Any questions at this point? Awesome. So then it says, suppose a second satellite passes through a point with rectangular coordinates of this right here. Are the two satellites at risk of ever colliding at this point? And explain. All right, so in order for me to compare anything, I need to take those rectangular coordinates and put them into polar coordinates. So how do I find the radius if I have my rectangular coordinates? What do I do? Okay, so x equals r cosine theta, y equals r sine theta, and you can get to it that way. There's a much easier way just to get to r. Square root of what? Isn't it just the Pythagorean theorem? Square root of x squared plus y squared? So that's the square root of 1.5 squared plus negative 3 squared. So that's going to give you, I'll just give you that one too, because 3.354. So that's the radius. I need theta. How do I find theta? Tangent inverse of y over x. So theta would be about 296.565 degrees. So that second satellite has a point of 3.354, 296.565 degrees. So there's a polar coordinates that it's talking about, saying that suppose the second satellite passes through this point. Is there any risk that it would ever collide at that point with the satellite we've been talking about? What could I do to see if that would happen now that I have this? So what? I could do systems of equations. Yes. I don't have an equation though. And I could make one, but that would work. If they are going to collide, what they would equal each other, right? Or even so I got to see if they're going to equal each other without a system of equations, because I don't have an equation. What else could I do? Because I have one equation. I could. Now, if I was actually on a computer, then yes, I would totally draw it. But with our little graphs, we're not going to be accurate enough. So we need a mathematical something. Don't I have that equation up there? I can substitute it in there, right? And so is it going to be easier to substitute r or substitute theta? I'm going to go with theta. Like, you could do r, but I think theta would be a little bit easier. So for my first satellite, or the original one, the first satellite, I can say r is equal to 4 over 4 plus 3 times 296, blah, blah, blah. That would be something that would be stored in your calculator. And I did store it in my calculator, by the way, this time for real. And then once you figure that out, what you get, oh, I'm sorry, 3 sine of that. Yeah, not just the angle stuff. Oh, come on. 3 times the sine of that angle, not just the angle. Here we go. That gives us the right thing. So what we get then is we get that r is about 3.038. So our ordered pair would be 3.038 and then 296.565 degrees. So given these 2 points, is there a risk of them colliding at that point? No. Okay. Especially if the radius, we're talking, tens of thousands of miles. So I don't think that the satellite would be big enough where the difference would matter. Okay, we good? Yes. So yeah, these are the two that we're comparing. Yes, those are the polar coordinates because we have a radius and an angle. They gave us this one in rectangular coordinates, and we had to convert. So we got to know how to convert. Okay, questions? All right. Now I want you to look at this construction model down here. It says boom cranes operate on 3-dimensional counterparts of polar coordinates called spherical coordinates. A point in space has a spherical coordinate of this right here. That's r theta phi, so you know that this is phi, where r represents the distance from the pole, it's the radius, theta represents the angle of rotation about the vertical axis, and phi represents the polar angle from the positive vertical axis. So given a point in spherical coordinates, blah, 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 find the rectangular coordinates. So I'm just going to give them to you. It's not anything I expect you to find right now. I just wanted you to see how these things work. Like this is the boom crane, right? So you have an angle that comes out this way, right? And then it also swings back and forth. So this is phi that comes from that vertical axis. That's your angle that rotates out that way. Then theta is the one that's going to rotate left and right. And then the radius would be like how long it is. So even if the guy operating the crane doesn't understand the whole polar coordinate system thing, whoever's programming this thing has to, right? Somebody's got to in order to make all this stuff work. That's how you get it exactly where you need to be. So I just wanted to, again, for you to see that there's, you know, applications, and next time you look at a crane, I want you to think about the ways that those angles work. And I'm going to give you the coordinates. This is what they would look like. So your rectangular coordinates x, y, z become r sine phi cosine theta, then r sine phi sine theta, and then r cosine phi. I'm not testing you over that. I'm never going to ask you that. I just want you to see that there are relationships between these things. Okay? Any questions at all? So I'm going to give you the assignment. There are 4 polar application questions on it. Again, just because there's words does not mean they're more complicated. The one we went through, that one was the most complicated. These are not like that at all. You're going to have to graph a little bit. You're going to have to look at your reference sheet so you know what they are, but you'll be able to do this with no problem. Okay?